understand. So we'll now try to understand polynomials like in R of X. So whenever we talk of a polynomial, we will by default uh, understand that it belongs to R of X or uh, C of X, as the uh, need might be. So uh, first, I want to tell you a bit of heuristics about polynomials that we will need while dealing with them. So basically, you can think of a polynomial in terms of like a few ways. You can think of them in terms of their roots. You can think of them in terms of functions in X. You can think of in terms of their factorizations, and also very rarely you can think of them in terms of the coefficients. So I'll just like it as functions, as roots, in terms of roots, of factorizations, of the coefficients. Like a lot of time, the point of the problem is moving from one interpretation to another, and yeah, that's a part of how you solve problems. And some stuff that which we will like get to know via the lecture is
Aryan,
like, and which is like essential.
Aryan, your voice is breaking a
Yeah.
little.
Uh,
Your voice is breaking a little.
Hello. Yeah, I said hello again. Was that better?
No, actually,
Hello.
that wasn't audible. Yeah, okay, this one was audible. It's breaking a little.
Okay, okay. Uh, I have no idea how to fix. Am I audible now?
Yeah, you're audible.
Hello. Okay, okay. Tell me if there is a problem. Uh, Other technique is like use, like we want to know where and like what understand polynomial is. I just like explain them in a short while. Uh, we will often use arguments relating to like of roots, use them for like in bounding arguments. So you also need to know like how to use the triangle in it. We will use difference a lot uh, because it helps in tackling situations
Aryan, your voice is
when you
breaking quite a bit.
need to. Okay, yeah, try changing internet. Give- Hello. Uh, is the voice better now? Hello.
Yeah, it does seem better.
Okay. Uh, yeah, I did switch internet. Yeah, so I was like talking about general methods you might require. So yeah, we'll like use differentiation a lot. It helps with like tackling situations where you have like roots with multiple multiplicities, and we will use something like mean value theorems and like IVT a lot. Uh,
Aryan,
and other than that,
your screen is just showing the meat for now. It's not showing your jam.
oh, I'm dumb. I forgot to like share. Sorry. Yeah, is it good now? Is it
Yep.
good now?
Yeah.
And other yeah, and other stuff is like you will need like Lagrange interpolation. That's like really important and like we use it a lot. And some other tips are like you need to know how to like, uh, uh, manipulate coefficients. It's more, it's very rarely. And finally, more like analysis-based techniques. So like I'll start with so I like first before going into any problem in the symmetric polynomial, so that like it's not really essential to know, kind of useful to know. So I thought I would just like mention it, and also like please Rohit hand on complete and
Your voice is breaking again.
uh, well hello, did that is that good? Was that better?
Yeah, it's good now, but it just broke in the middle.
Yeah, am I like should I repeat myself what I said in between?
Yeah,
Uh,
that would be great.
okay, yeah. So I was like just saying like please read Rohan's handout on polynomials. If you are like haven't already, it's like quite good. Like it covers both like algebraic aspect and number theoretic aspect of like polynomials used like in olympiad. So please do give that a read. Uh, okay. I'll like start with just telling you a bit about symmetric polynomials, right? And okay, see, so like a polynomial n minus one, just a n to the n plus a n minus one into the n minus one up till a naught, right? And suppose it has like roots alpha one as like summation of the all the alpha I, and this is like minus a n minus one by a n. You define the second symmetric sum as something like this, and it becomes a n minus 2 by a n, and it goes on like, and you define sigma 3 as the third symmetric sum as something like this, alpha I alpha j alpha 2, and it becomes like a n minus 3 by a n, and so on, right? So these are like how symmetric sums work, and this is basically Vieta's relations. And the main theorem that you should know from here is basically the fundamental theorem of Sympholy of elementary symmetric polynomial. That is any symmetric polynomial uh, uh, in say x1, x2 up till xn can be expressed uniquely as a polynomial in sigma 1, sigma 2 up till sigma n. Yeah, a symmetric polynomial is any polynomial that like remains invariant even if you like change the permutation of the variables. So like something like if you say define p of xyz as like xy plus yz plus zx, right? And you look at p of y comma x comma z, it's the same as this, right? So this is like a symmetric polynomial. So the fundamental theorem of elementary symmetric polynomial states that any symmetric polynomial in like say n variables, x1, x2 up till xn, can be like you can find a unique polynomial q in sigma 1, sigma 2, sigma n such that this holds. So this is quite useful to know, hence I just mentioned it. Uh, we'll like use this a
Sigma
bit.
1, sigma 2, so on are the Newton
Yeah,
terms found by a polynomial of roots x1, x2, xn.
yeah, they are the sigma ones are like sigma k are like the state symmetric terms of xi. So like sigma one is sum of all xi, and sigma two is like x1 x2 plus x2 x3 plus da da da. So we'll use this a bit in like what I just mentioned. We might will use this a bit tomorrow when I like try to cover two variable poly. For now we will like begin with some problems, and like we'll look at like polynomial equations and like some general methods for solving them. I'll just give the header, uh, poly equations. So like poly equations are of the form basically find all polynomials in Rx, is that say this is a random uh, a random equation holds and something like this. So some general methods are like that you might require are like firstly it's important to treat the polynomial for fe at least like a fe at least for a while to get like say some obvious substitutions, some basic like what are the roots of it and so on. Another way is like another important thing to remember is like often you find like in a polynomial equation like every variable is like kind of wrapped, as in the polynomial equation reads like this. So like you can substitute x equals to something, but you can you the x is not free in here. The x is always like embedded inside a p of x, right? So in those cases you can like differentiate both sides, and that helps in isolating an x. So suppose like in an expression if you have something like p of sine x equals to something is given. So like if you differentiate this side, this gives you like p dash of sine x into cos x, right? So now equals to the derivative of the other side. So now this has given you a freedom to like make cos x what you want. So this gives you an added degree of freedom. So remember this. This is quite useful. Another thing to keep in mind is like deal with size of the root. This is quite important. Size of the complex root, what you can say about their absolute value. Basically, we will solve this problem using this idea. This is quite classical. I just left it this so that like everyone to just to make sure for sanity check, like everyone knows this, right? Another important factor and thing is I'll show this in a problem. Like often it so happens like you are asked to find solutions to some fe, and the solutions, if the solution is p of x, it happens to be a polynomial in some lower degree solution. Like suppose if anyone remembers like the INMO 2020 number 2 problem, it was like you had to find a solution like P of sine theta plus cos theta equals sine theta minus cos theta, I guess. Yeah. And like so in those cases in that problem the solution was like P of x equals to any even polynomial of uh 1 minus x squared whole square. sorry, 1 minus x square. So like this is one idea you need to remember is like when you feel the solutions are of this kind of form with a polynomial of a lower degree solution, then what we do is like we guess the solution with the minimal decay. In this case, we guess 1 minus x square is a solution, right? And we prove that in this case qx equals 1 minus x square, and we prove that for some constant, say k, qx minus k divides p of x, and then we induct on degree. So if this sounds a little bit cryptic, we will like solve the INMO problem from 2020. So it'll be a lot clearer than now. I'm just like telling you the heuristic now. Uh,
Oh, why do we show q of x minus k divides p of x? Like, what does that say?
yeah, like basically, what I'm trying to say is you can write p of x as, suppose you can write p of x as 5 q to the 3 plus 4 q to the 2 plus q plus 1, right? So in this case, you would have q minus, sorry, I messed it up. You should have like written qx divides px minus k for some constant. Yeah, sorry. So in this case, you have like q divides p minus 1, right? So, and then you can like, you can probably show that p minus 1 also like uh, satisfies the equation described, and then you can induct down on degree. We'll come to this when we like solve the INMO problem. Uh, that will be much more clear then. Okay, so like first, the first problem I want to do is like the most classic. Find all polynomials uh, going from Rx to Rx. Uh, why am I writing like this? Yeah, so like find all polynomials belong to Rx such that f x squared equals like fx into fx minus 1. So like this is a very like classical problem. I just like put this in the set so that like no one would miss out if no, if someone does not know about this. So like how do we solve this problem? It's like we will look at roots of the uh, roots of f and look at their absolute values, their norms. So like suppose alpha is a root of f, right? Suppose this holds. Then like immediately note that if you plug in x equals alpha, you get f of alpha squared equals 0, right? And then if you plug x equals alpha squared, you get f of alpha to the 4 equals to 0, right? So then you get something like alpha square, alpha to the 4, alpha to the 8, and so on, alpha to the 2 to the n is always a 0 of f, right? But f can only have finitely many zeros, right? So this basically tells you that alpha equals yeah, so this basically tells you that alpha equals 1 is, sorry, norm of alpha equals 1 is the only possible choice. Otherwise you have like, if alpha's absolute value is more than 1, then it's like an increasing sequence of norms, so again infinitely many roots, and if it's less than 1, then the norms are like strictly decreasing, and again you have like infinitely many roots. But also note that if alpha is a root, sorry, if alpha is a root, uh, also have something like alpha plus 1 is a root. Sorry, yeah, you also have that alpha plus 1 whole square is a root. If alpha is a root, then alpha plus 1 whole square is also a root. So for this, you substitute x minus 1 equals to alpha, right? So this basically tells you that mod alpha, again from the above argument, we can again conclude that absolute value of alpha plus 1 is also 1, right? So basically we are trying to find trying to find all complex alpha such that mod alpha equals mod alpha plus 1 equals 1, and this is basically alpha equals omega and omega squared. So the basically the polynomials we are looking for are of the form x squared plus x plus 1 into n for some positive integer n. Does anyone have any doubts about the solution of this problem? I
How
didn't.
did you finish after finding that alpha equal to omega or omega square?
So like it's like easy to finish from here, to be honest. Like you can figure out the details for yourself. The main like you so like the only possible roots are like omega and omega square, and I mean you can work it out for
Ah,
yourself. Like that's
yes,
not
got
really
it.
the important part to talk. So having done that, we like move on to a more difficult problem. Right. The main idea about the previous problem was like you basically learn how to size bound roots. That's the basically the main point of the problem. So we'll carry forward the same idea in this one. So this problem is 2005 A1. The problem reads as follows. Find all uh, a comma b belongs to z such that there exists a polynomial p of x belongs to z of x such that x square plus ax plus b into p of x is of the form x to the n plus cn minus 1 x to the n minus 1 plus uh, c1x plus c naught, where every ci is minus 1 or 1. Does everyone understand the statement of the problem? Find
Yes.
all Okay, find all integers a comma b such that there is a integer polynomial such that x squared plus ax plus b into p of x is of the form x to the n plus 1 or minus 1 x to the n minus 1 plus or minus of x to the n minus 2 and so on. So like this problem is also like kind of falls straight apart like if you try bounding the root, right? So like suppose this polynomial, give it a name, say it's q of x, right? So suppose let alpha be uh, a zero of q of x. So note that you can.
Aryan, can you give 1 minute to solve?
Okay, yeah, sure. Yeah, give it a go, surely.
The roots of q of s lie between minus n comma n. Do we use this?
Come again, please.
Okay, no, sorry. I misread it.
I put the problem statement on the screen if anyone did had a problem in like understanding the wording. Uh, I do plan to cover a lot of problems today, so I'll just maybe give you 2 more minutes. Okay, I think let's just get on with the solution. The problem is like quite instructive, so like even if you haven't like really tried it a lot, it won't be much of a problem. Like you can like take this the methods we use in this problem as like motivation to solve other harder problems. So like what we will basically do in the problem is like size bound, like blindly size bound, right? So like suppose say z is a root of q of x, right? Q of x is the resulting polynomial. So like you can immediately write something like zn z to the n equals minus of c to the n minus 1 x to the n minus 1 plus d to the n minus 2 sorry cn minus 2 x to the n minus 2 plus dot up till c1 x plus c naught, right? So now what we will do is like here comes the main part. We will take mods, like we will take absolute value on both sides. Note that you do not know what cn minus 1 might be, but you do know for sure that it has to be like its absolute value has to be plus or plus 1, right? So if you take its mod and like use, and this is basically a sum of a lot of terms, so you can use like triangle inequality on it, right? So this makes the expression more like you can handle it in a better way. Like if you take mod, it becomes mod z to the n equals mod of cn minus 1 x to the n minus 1 plus cn minus 2 x to the n minus 2 plus up till c1x plus c naught. And using what do they call it, triangle inequality, you get, since this is at you can, this is less than or equal to more absolute value of x to the n minus 1 into absolute value of cn minus 1, which is 1, right? Like not right, the absolute value of this is also 1, so I'll just like omit it and write x to the n minus 2 plus up till 1. right? So now if you just like, oh, I used x z here and like I use x here. So like if you just uh, manipulate the expression, it becomes okay. I'll save you a bit of algebra manipulation because I worked it out already. So it comes out to be this. If you like just like manipulate it, right? So it comes out to be this. Uh, so what does this expression tell you? We assumed z was a root of q of x and we used bounds on z, and we understand that this must hold true, right? So what does this tell you about z? What happens if z is mod z is uh, like at least 2? uh, Anybody like to say?
Can't be.
I couldn't hear you.
It can't be greater.
Okay, I still couldn't hear you, but okay, I'll just like say what I meant. Like, note that if z, mod z is at least 2, then this inequality cannot hold, right? So this basically just tells us that mod z has to be uh, less than 2, strictly less than 2. So now the problem is a bit weak. So like this claim alone is like sufficient to solve the problem. I'll just like tell you about the details a bit. I'll just like outline the details you can solve for yourself, right? Also like note that the polynomial was like ax squared plus ax plus b into like x to the n minus 2 plus, sorry, it was like p of x equals something. Suppose the p of x had like the constant term as say uh, d, right? The constant term of px was say t, and the constant term of this thing is c naught, right? So you have something like bd equals c naught, but you also know that both are integers, so you directly get mod b is 1. So, like, I mean b is plus or minus 1, right? So from now you also know that what are the roots of x squared plus ax plus 1 equals 0, right? So it is 1 second. The roots of it are like mod a plus so now what you just need to do is like again bound mod a. Remember that a is an integer. So like when can this quantity like become greater than 2? So like if you just do a bit of algebra, it turns out that if mod a is at least 3, uh, then at least one of the above roots is uh, has mod value like more than 2. So that would be a problem. So now you just need to sort of bash out the cases for alpha a equals this these guys and b equals plus or minus 1. This was the rather uninteresting part of the problem. I'm sure you guys can like figure it out on your own if you just like try. The main part of the problem was this, like was this the bounding part. And this is also like it basically this problem is a good example of how you need to use triangle inequality and bounding of size of roots and why it's so important, right? Okay, we will move to the next example. Does anyone have any questions here? Anyone have any questions or doubts from this solution?
No.
All right. So the next problem we do is InMo 2020 problem 2. Uh, so like here's the problem statement. Give it a read. Uh, it's probably just better if I show you the problem statement instead of me. like trying to explain, or I could do that too as well. Okay, so the next problem is in more 2022. So the problem goes like, suppose you have p of sine cos. Okay, wait, I messed up. Just cos theta plus sine theta. Right? P of cos theta plus sine theta equals p of cos theta minus sine theta. Then prove that for all theta belong to real. Then prove that p of x is an even polynomial in 1 minus x square. Okay. So basically, this problem like helps you in like getting a grasp over most of the concepts that you like really need in solving polynomial equation type problems, right? So like the first thing you notice from the problem statement is like, if p of x is a solution, then so is p of x minus any constant, like p of x shifted by any constant, right? Do you agree with this? So this means that we can sort of like force p to have a root at any point. So like, also note that you need to prove that it is a polynomial in 1 minus x square, right? So as I mentioned, like if p of x is a solution, p of x minus like shifted by any constant is also a solution. So we will assume p of 1 to be 0 by default, right? This is because like 1 minus x square factors into like x plus 1 and x minus 1. One of them has 1 as the root. And now we will try to prove that 1 minus x square whole square divides p of x, right? So like, is the intention clear what we are trying to do? As I mentioned like during the beginning of the lecture, like here the solutions are of the form of a polynomial in a small degree solution. The small degree solution here is 1 minus x square. And any solution is a type of polynomial in 1 minus x square, right? So what we will do is like, we will show that 1 minus x square divides the solution, like p of x shifted by some constant. And then we will induct down on degree. So since p of x shifted by any constant also works, we will just assume p of 1 to be 0, right? So next thing, if you like substitute pi by 2, you get something like p of 1 equals p of minus 1, right? Which is equal to 0. So this directly gives you like 1 minus x square divides p of x, right? So this is how, this is like, so you got one factor of 1 minus x square. Now we just need to double it. So other words, we need plus 1 to be a double root of p of x and minus 1 to be a double root of p of x. So when you see double roots, the first thing that you should think of is differentiation, right? Also, like, why differentiation is very good in this context, note that again these things are like the only places where you can like plug some value of theta. This is the only freedom you've been given in the problem, right? But even then, like whatever you can substitute in these places are like still within p of x, like within the like embedded inside a p. So not, you don't know a lot about the functional values at different points, so it's, you're still kind of stuck. But if you like differentiate both sides, right, then you would have a extra term of like of the form, this becomes differentiate cos theta, it becomes minus sine theta, and differentiate sine theta, it becomes cos theta. So on the LHS you would have a term cos theta minus sine theta into p dash of cos theta plus sine theta. The left term is important because it gives you a lot more freedom, right? I'll just do it. So differentiating, you get p dash cos theta plus sine theta into cos theta minus sine theta equals p dash cos theta minus sine theta into minus sin theta minus cos theta. Right. Okay. So now again we can like substitute different values in it. If you like play around for a while and if you like say substitute say theta equals 0, that's directly gonna give you like p dash 1 equals, if you just like do it, and then this basically gives you uh like p dash 1 is also 0. And you also know that since p1 equals 0, you know that 1 is
Oh,
a repeated root. Yeah,
how does
so
this give p dash 1 equal to 0?
you just substitute theta equals 0 in this big thing.
No, like after this, p dash 1 equal to minus p dash 1, then how p dash 1 is 0?
It's x equals minus x equals 0. Did you get?
Ah, okay. I was
Yeah,
thinking it minus 1.
yeah,
Sorry.
no issue, no issue. So like this tells you that 1 is a repeated root. So like you can again like play around for a while and you can like make some substitutions and you get like minus 1 is a repeated root as well. Right. So using this you can finally prove that let me go to this side. Using this you can finally prove that 1 minus x squared whole square divides p of x. All right. So does this finish? Are we done? We proved that if p of x is a solution such that p1 equals 0, then 1 minus x squared whole square divides p of x. Does this finish the problem?
We still have to enter.
Your voice is breaking. I
We still
couldn't
have to
understand what you
induct.
said. Yeah, but like, why does this just does not finish? Uh,
Oh,
Okay, yeah, what you just said actually is good enough of a reason. Basically, we kind of still need to prove that px divided by 1 minus x squared whole squared satisfies the problem. That's basically what we need to prove. And that is easy. You just divide both sides. All right. Yeah, I was being stupid myself for a minute. So we just prove that this relation holds, and now it's kind of like very trivial to see that if p of x is a solution, then this thing is also a solution. So yeah, you just induct down on degree. So induct on degree. So if p of x was of degree 2n, then this thing is of degree 2n minus 4. Yeah, you can just like check the details. I'm not really interested in the details. uh, right, yeah, so that concludes this problem. Does anyone have any questions from this or doubts from this solution?
After p1 equals 0, how did you conclude 1 minus x squared divides p of x in the
Oh, you
last line?
plug it in the, can you repeat what you just said?
Okay, okay. In that, when you had written p of 1 equals 0, how did you conclude 1 minus x squared whole square divides p of x?
First, you prove that 1 minus x squared divides p of x. If you like plug x equals pi by 2 into the equation, right? What in the original equation, what you get is p1 equals p of minus 1. All right. So if you assume p1 equals 0, then this tells you that 1 minus x squared divides p of x, right? So it's not a repeated factor yet. To get the repeated factor, you differentiate, right? So after differentiating, you get a much more, like you have a lot more
Okay, I
freedom as
understood.
in.
Yeah, yeah, I understood.
All right. Okay. If anyone does not have any more doubts, I'll just move on to the next problem. That is USMO 2019 problem 6. Please read the problem. It's on the screen. Right, so I'll like start solving it. Uh, do you guys like want maybe 5 minutes to try the problem? Uh, it's enough time. Okay, maybe like look at the problem and like try to get a feel for it in like 2 3 minutes, and then like tell you the solution after that. Move to the next page. Okay, let's like start with the solution of the problem.
It is even, right?
Could someone say anything?
Like the polynomial is even.
Yeah, that is true. Yeah, that's really good progress if you have found that. Uh, keep in mind the non-zero part though. Like you are not allowed to directly substitute x equals zero or something like that. Keep that in mind. Okay, let's begin with the solution. So, so it is given that like this relation holds p has like real coefficients, and this relation holds whenever 2xyz equals x plus y plus z, and xyz is all are non-zero, right? So like if you think of the like consider a three variable expression as xyz into RHS minus LHS, right? So if you consider a three variable polynomial sort of in like uh, as like xyz into RHS minus LHS. So basically, what I'm saying is xyz into or just say something like x px plus y py plus z pz minus xyz into p of x minus y plus p of y minus z plus p of
I think your screen is not loading as what you are writing.
what happened?
Uh,
Uh,
the thing you are writing is not visible
do
on
you
the
see the
Yes,
chat.
screen now?
then
Do you see the screen now?
we see the screen, but the writing is not visible.
Uh, that is unfortunate. I Okay. Let me unshare and share. Uh, okay. Do you see the screen now?
Yeah.
Yes.
Okay. So like if you like look at a three variable polynomial, say q x y z, that's equal to like x into px plus y into py plus z into pz minus xyz into the RHS. Basically xyz times LHS minus RHS, right? So what can you say about the this like equation, like this polynomial? So like one thing about polynomials that you should know, and that's a really good property about polynomials, is like they are always continuous, right? So if any polynomial relation is true for infinitely many x, right, then that polynomial equation is true for like all x, right? So if you like think about it, this polynomial equation is like, so q of x comma y comma z equals 0 is true for all xyz. Yeah, 2xyz equals x plus y plus z, right? So like by continuity you can just say that it is always 0. Do you get the argument?
Yes.
Right. So like why, if anyone has doubts, please ask. Like this is the most
Also,
important part of the solution. Yeah, yeah, Sumit, just say.
like, do we need to say that? Like, isn't that obvious? Because like we are just taking because those two things are equal.
I didn't get you.
Like in the question only it was stated, no, that this thing is equal to
They are,
zero.
yeah, they are equal when this holds.
Ah,
This
okay.
condition holds.
Okay, yeah, got it.
Repercussion.
Yeah, sorry.
Oh, by the way, you guys can like find the sort of a handout or problem set which I sent like on in the announcement channel in the Discord. So like take a look. It has the questions and all. I just really meant it to be a problem set sort of, because Rohan has already like written a very good handout. So writing a handout doesn't really make sense anymore. Okay, so this is the like the main point of the solution. Like q of x comma y comma z equals to 0 is basically true for all this, right? So this means that you can not only substitute xyz equals reals bar 0, you can basically substitute xyz as anything. You can even let one of them be 0, right? So this is basically the main part of the problem. Other than that, it's basically a functional equation. You just have to substitute values and wait, right? So from here directly, if you plug in x equals x, or just like uh, if you plug in x comma minus x comma 0, you will directly get that it's even, right? I'm just like not working it out. You can just do that on your own. You will directly get that it is even, right? So uh, now it boils down to, now from now it basically boils down to sort of bashing it out with like value substitution. So like there are a few ways in which you can do it. I'll like just show you one way. Like you can, from here on there are a lot of finishes. Like one finish includes say this is a finish, plug x equals a, b, sorry, y equals 1 by a, and z equals uh, a plus 1 by a. Yeah, right. And basically also like from here, maybe you could all kind of guess the solution as well, right? So the solution is supposed to be p of x equals uh, k into x squared plus 3. Yeah, so as you can see, degree is always 2, right? So like one finish is like if you plug x equals to a, y equals to 1 by a, z equals to a plus 1 by a, right? And in the resulting equation, like look at leading coefficient in the resulting equation. I'll not work out the details as usual in the resulting equation. This is one finish. Another finish is like this finish basically shows the true power of what we just did, right, regarding the continuity argument. So what we do is like we plug x equals x, y equals I by root 2, and z equals minus I by root 2, right? And then if you like sort of like rearrange the terms, you get something like p of x plus I root 2 plus
Oh, the
p of,
polynomial is defined over reals. How can we substitute complex number?
yeah, that is the main like point of what we just did, right? Think of
But
p of
that's
x,
what.
like real numbers are also complex numbers, right?
Yes. But
So
like
like
in
what we just, yeah, let me explain. So like what we did while proving this, like the continuity argument was like it holds true for all 2xyz equals x plus y plus z. Xyz can be anything here, right? Like it is not only, so like think of it like this: q of x comma y comma z is a three variable polynomial, right? Suppose like consider it in c of xyz, right? It is true for all xyz belongs to reals, like, and satisfying this. So basically you can just like extend it to complex numbers, for all
okay.
complex numbers satisfying. If this seems hard to you, think of it as two variables, right? You can uniquely determine z given x comma y. Agree? Do you agree? Given x and y, you can like just set,
Yes.
right, 2xyz equals x plus y plus z, and like figure out what z is. So like you can think of a two variable polynomial, say r of x comma y, right? In terms of uh yeah, you can think of r of x comma y as what we defined x comma p of x comma y comma z. This is basically, this is like u of x comma y comma, let me just solve the equation x plus y plus z. So z is x plus y by 2x minus y. Okay, yeah, x plus y by 2x minus y, right? So this is a polynomial. This is again r of x comma y is a polynomial with real coefficients, right? And this tells you that r of x comma y is equal to 0 for all real x comma y, right? So it must the so rxy must be identically 0 for xy complex numbers as well, right?
But
So
how
yeah,
do we get continuity in complex number? Because like if we take norms, it like
no, no,
varies
no, no,
so
no,
much.
no, don't think like that. Like, okay, suppose how to explain this? Like, if a polynomial, can you think of a polynomial? Okay, so like suppose it was a complex polynomial, like, and you have like a factorization of it, x minus alpha n, and I am telling you, suppose this is a polynomial p of x and in complex, and like with complex coefficients, and it has like a factorization x minus alpha 1, x minus alpha 2 up till x minus alpha n, right? And I am telling you that p of x is 0 for all real numbers, right? If x is real, p of x is 0, right? So it has infinitely many roots then, right? Then p of x must be identically 0, right? It's basically the similar, it's basically completely the same case when you have like two variables. I'm telling you, like for all two variable for all uh, real, what do you call it, pairs x comma y, you have r of x comma y equals 0, right? Hence, even if like r of x comma y as a two variable polynomial in x and y must be identically 0. So even if you pick x equals some complex number which is not like purely complex number, so like, or not even purely, why am I saying purely, like if you say pick x equals 1 plus I and y equals 1 minus I, r of 1 plus I comma 1 minus I is still 0. Do you get the point now?
Yes.
Okay, just do it on the next page. So like or the page. Yeah, this was free. So like if you like just plug in okay, x I by root 2 and I minus 1 by root 2. Also, by the way, if someone is like wondering how am I getting these substitutions, it's kind of you need to know something and you need to like try something. Like this substitution is kind of well known for like the 2xyz thing. Also, like it is a T2 and rescue problem, so you should like expect to substitute somehow. uh, Rearranging, you get something like uh, minus 2px plus p of x minus I root equals p of root 2I. Okay. Uh, so if you put uh, these values and you rearrange it, this gives you this after rearranging, which I obviously haven't done. So like, what does the LHS look like now? Can anyone tell me what does the LHS look like now? Okay, just tell me if p of x is degree n. Sorry, what is the degree of LHS? Anyone?
Can you rephrase your question? I didn't hear it.
This equation holds, right? Now I'm telling you, suppose p of x is degree n, right? Then what is the degree of LHS? Like highest degree term of LHS. Note that LHS is something a variable of a function in x, but RHS is constant. So what is the, so that means that basically LHS must also be constant. But what is the highest degree term of LHS? Because LHS is like still a polynomial, right?
N only.
Yeah,
Oh. N minus 1, because like
it's
n cannot be
right. N minus.
at least n minus or n.
um Yeah, that is true. Basically, like it's not n minus 1, it's n minus 2 actually. So like how am I, okay, one another way to see this is like if you like know finite differences, then you will be like able to like understand this very clearly, right? I'll just tell you, come back to this after I discuss finite differences, which I'll like just do now, right? So like you can either like work it out on paper or like you can just do it like this has degree at most n minus 2, right? So this directly gives you, and this term has degree n minus 2 at most. This gives you n minus 2 is like at most 0. So this basically gives you n is at most 2. And now you can like basically manually tackle the cases. So
Okay, you are
like,
asking for the entire LHS degree.
yes,
You are referring to the degree of the entire LHS, right? After we work it
yeah,
out.
p of x plus I, yeah, this thing.
Okay, okay.
Not, this is RHS. RHS is p of root 2I. Uh, does anyone have any questions regarding what we just did, the USMO problem? Uh, if no one has any questions, I'll like just move on to Lagrange interpolation and finite difference. I'll just mention both of them. Okay, I guess I'll move on because I'm kind of like short on time. If you have any doubt, please do ask in between. And if you like find it out after class, you can just like ping me on Discord. Okay. 1 second. Yeah. So Lagrange interpolation is like a really important method, like for a lot of purposes. Like I'll just tell you the statement first. So suppose let p of x be a polynomial of degree at most n, right? Let x1, x2, xn plus 1 be distant reals. Then it turns out that you can explicitly say that p of x equals summation I equals, okay, let it be like x naught x1 up to xn, right? It looks better. I equals 0 to n f of xi into I is not equals to j, xi minus xj. Sorry, yeah, it's correct actually, right? Minus x. So this is the formula for Lagrange interpolation. So like take a moment to understand what Lagrange interpolation is basically telling you. Like it tells you that if you have a polynomial of degree at most n, right, and if you know its value at n plus 1 different points, right, then you can completely like characterize the polynomial. You can like pin down the polynomial. I'll not prove the formula, of course. You can like just read the proof from somewhere. The linear algebra proof of this is rather interesting, so like do try to check it out somewhere wherever you like get it. It's like easy to find. So like I'll mostly focus on like uses of Lagrange interpolation. Right. So like one use of Lagrange interpolation is like if a polynomial of degree d has d plus one rational points on it, then it has a rational coefficient. By rational points, I mean a pair x comma y such that x and y are both rational. Right. So how do you make sense of it? So suppose like x1, x2, xn plus one are all rational and their functional values are also rational, right? So like the entire thing is also rational by like by default sort of, and you get your conclusion. Other things I want to, these are like important things about Lagrange is like often you need to like bound the terms, right, to get useful results. And two other important like tidbits sort of you might want to keep in mind, like we just mentioned like interpolating a n degree polynomial of degree at most n on n plus 1 point, right? But what if we interpolate the polynomial on n plus 2 points, right? Because n is obviously at most n plus 1, then you know it for sure that the degree x to the d plus 1 coefficient that you get is equal to 0. So that is also like useful. It might give you an identity. Another one is like this is less often seen. It's like if you Lagrange interpolate on a constant polynomial, right? It might sound weird, but it might often give you good results. So like I will jump to the, okay, yeah, I'll also have to mention what finite differences are. Uh, so like finite differences, you should just like know it. It's not that important, but well, let's just mention it. Okay, so let's do it on the next page. Finite differences. Did anyone have any trouble understanding Lagrange interpolation? Any questions?
No.
Okay. No, so finite differences are like, yeah. Suppose you have a polynomial p of x, right? So for any x, you define the first order for finite difference to be p of x plus 1 minus p of x, right? Note that if this has degree n, this has degree n minus 1, right? So often people call it finite difference with step 1. Like if you just say a finite difference, it means by default with step 1. So like I can say like finite difference with step 5 is p of x equals p of x plus, sorry, is p of x plus 5 minus p of x, right? So this is, yeah. So this is basically first finite difference with step 1. Then you have like second finite difference is like del of p of x, right? So this is basically p of x plus 2 minus p of x plus 1 minus p of x plus 1 minus p of x, right? So this becomes p of x plus 2 minus 2 of p of x plus 1 plus p of x. This is step 2. Right, sorry, this is like second order finite difference. And henceforth, you can like have third order, fourth order, and so on. Right. So like the only thing that's essential from here is the identity that you need to remember. It's like often quite useful. Right. So uh, if you like let CK denote the kth order finite difference at 0, right? So like P0 is P naught, P1 is P1 minus P naught, P2 is P2 minus 2P1 plus P naught, and so on. Right. The equation that you need to remember is this. Uh, for proof, just expand. So this is basically the only thing you need to remember. Right. Anyone have any questions from here? What I just wrote?
How does the first finite difference lead to expansion?
I did not understand. Can you like write in chat maybe? I'm following the chat now for a minute. Or maybe just tell me once again what you just said. Hello. I'll just go on, I guess. Uh, so like now that we know what finite differences are, and I just like define.
Um,
Yes.
he asks, can you explain how you got x minus 1?
X minus one. Well.
Oh, n minus 1.
Oh, like the constant term in here is like. Oh, sorry. Actually, you can just like work it out on your own. To be honest, like the highest degree term in here is like a. Suppose the leading coefficient is an, right? So it has like the leading term is second. Let me just do step other. Uh, is like an into x plus 1 whole to the n, and the leading coefficient here is an x to the n, right? If you like open this with binomial theorem, then this give you an x to the n plus stuff that is uh, with degree x to the n minus 1, right? Minus an x to the n, right? So basically this and this like just cancel each other, and you are left with stuff with degree uh, x to the n minus 1. So this reminds me, yeah, this reminds me that I should tell you that if you have a degree n polynomial, right, and if you uh, take finite difference of it at any point n times, then that gives you n factorial. If it's monic, sorry, degree n monic polynomial, and if you like take a finite difference of it n times, then it gives you n factorial. How is that true? Like just look here, right? So when we take the first finite difference, what's the leading term now? The leading term is n choose 1 into x to the n minus 1, because similarly the an minus 1 into x to the n minus 1 term gets cancelled out, right? So what just happened is degree reduced by 1, right? And the like the leading coefficient got multiplied into the into n. So like when you now take a finite difference of this, the new term is n into n minus 1 into x to the n minus 2, and so on, right? So like when you take like n times finite difference of this thing, you get this. So this is just something useful to know, right?
Oh, what, like after taking finite difference, what is equal to n factorial basically? The degree?
No, no, no. The value. We are taking a value. No, we're getting a value whenever you do
Ah, okay.
finite. Basically, the nth finite difference of a degree and polynomial is constant, and it's equal to n factorial. If the polynomial is monic, if it has a leading coefficient a to the a d, say, if the polynomial is like, sorry, not a b, a n, like the polynomial is has a leading coefficient an, then like just do it yourself. Like it's the same concept basically. Then you have an extra an here. I'll just like leave it out. You can like try that for yourself. It'll be probably an to the n, an extra term. Yeah, that's like you can work it out. Yeah, so like since we know this now, let me go back to the USMO 2019 6 solution. Right. So look at this thing once again, right? This is from the solution of 2019 USMO 6. Look at this expression once again. What is this? This is basically a second order finite difference with step I by root 2, right? Do you
Yeah.
agree?
Yes.
Yes, so like this has a degree n minus 2, but it is also constant, so n is at most 2. Obviously, you know, like the finite difference of a constant polynomial is constant, right? So, like it could have been possible that the first finite difference of p of x with like step I by root 2 was constant by itself. So the degree p is at most 2, and now you can bash. Okay, let's move to a new problem that is, let's solve problem 2. Please read problem 2. Problem 2 is from here. It's like tells you like let p of x be a non-zero polynomial with real coefficients such that p0 is 0. Actually, this is a superfluous condition. I should have edited it out. I forgot. P0 equals 0 is not essential for this. Prove that for any positive real number m, there exists a positive integer d such that for any monic polynomial qx with degree at least t, the number of integers k such that the inequality holds is at most degree t. I'll just quickly write this. I actually wanted to cover one more problem with this, so I might take like 7 8 minutes extra time. I wanted to cover like both one and two here. I'll do two first and I'll do one next. I'll just maybe take two more, like maybe a maximum of 10 minutes after time is over. Uh, okay, so the Iran problem, 2018 A4. I'll just repeat the statement. So what it tells you is like p of x is a real coefficient polynomial, right? Prove that uh, there exists a integer d such that d belong to n, such that if degree of a monic, and this is q is monic, right, is at least d, then number of integers k with pqk at most m for a fixed m is at most degree p. Sorry, at most degree q. Does everyone understand the question? Anyone have doubts with what the problem is trying to say? Okay, no, I guess. I'll move. So, like, first of all, note that the problem is a bit weirdly phrased. What I mean by weirdly is like, first of all, like, just try to solve the equation mod of py is at most m. M is fixed, all right. So, like, m is fixed. So, first of all, like, just consider the set S such that, like, say, y is a real number and py is at most m. So obviously y must be bounded, right? Because like if this set S was unbounded, like if y could be like anything, then you would have a problem because the if you like look at the sequence obtained by taking a value of a polynomial at an unbounded sequence, it becomes unbounded itself, right? So you must have y is bounded, right? So like in other words, like y must have like a boundary. So like you must have something like mod y is at least mod y is at most a for some real number a. Or in other words, you have something like the solutions to mod py at most m is a interval which is a subset of the form minus a comma a for some. So y is a subset. The interval in which y belongs to is some subset of minus a comma a. Other words, y is bounded, right? So now, did anyone have any problem in what I just said?
No.
Okay. So now, what the problem is basically trying to say that for all large enough integers, say, did I use n? No. So like for all large enough integers n, right? Like and any monic polynomial q of x with degree n, right? The number of solutions to q of x the number of integer solutions to q of x at most a is from the previous one is at most n. Number of integer solutions to. So now what we will do is like this is quite tricky. This is like the most trickiest part of the problem. We will Lagrange interpolate a monic polynomial q of x at points 0, 1, 2, 3, 4 up till n, right? Why we do this? Note that the polynomial q of x is actually monic. So like when you write the Lagrange interpolation formula, right, you can explicitly tell me what is the largest coefficient in there, like what is the leading coefficient in there, and we can equate that to one and use bounding to get some kind of result, right? So like you can obviously say something like yeah, so q of x is equals to summation I equals 0 to n q of actually like it's not like you have to like interpolate at just 0, 1, 2 up till n. You can interpolate at like any n plus 1 integers, right? So like if you in Lagrange interpolate at any integers xi where I runs through 0 to n, right? You can write this. This is the Lagrange interpolation formula, nothing special. Uh, x minus x by xi minus x. So now, what is the leading coefficient of q of x that you see from here? Do you agree with this? What I'm writing? This is the leading coefficient xi. Do you agree with what I just wrote? Does anyone have any issues? This is like just manipulate the terms, right? So like if you Lagrange interpolate q of x at any t plus 1 point, what you get is like the leading coefficient of the resulting polynomial is this. But you also know that this is 1, right? By the question, q was said to be monic, right? So this gives you an identity to work with, at least gives you something to work with, because there's like a lot of freedom in this problem, right? So like you write something like 1 equals summation I equals to 0 to n q of xi into I naught equals j 1 minus xi minus x2, right? So now what we will do is we will like use bounds on this thing, right? So you use the bounds kind of cleverly. So like note that q of xi varies, right? It is not fixed. But what we will do is like we will upper bound this. We will take maximum of like we'll upper bound this. Note that suppose given the values of q of xi, suppose n equals max I qxi, right? Suppose n be the maximum value of the qxi given, then you can write this as n times I equals to 0 to n multiplication j is not I 1 by x minus, right? So like what's next? Then again, like this product for any like I not for any like xi xj is like maximized when you pick them to be 0 1 2 3 4 up till n, right? To prove this you can just like work it out for yourself. It's like just a trivial fact. It's just like uh, easy to see. All right, so like in other words you can like bound this thing by uh yeah, by I factorial into n minus I factorial. Did you get this part? I'm like saying that like this value is like you can like minimize like you can use the lower bound most accurately when xi is equal to I, right? So yeah, so this gives you a bound, so now you can like use it to get, suppose you write it as n by n factorial, and it becomes basically summation I equals 0 to n nci, right? So this becomes 2 to the n, so it becomes 2 to the n into n by n factorial, right? So what does this give you? This tells us that n is at least n to the right. So this basically tells us that n is at least n factorial. Uh, uh, like this inequality holds, right? So now think about this. What does this like tell you? N was maximum of q of xi, right? Uh, Max I q of xi. So this basically tells you that no matter how you choose n plus one values of uh, integers, you can always find one integer value at which q of x has a relatively large value. Like n factorial by 2 to the n is some value, and like you can, if you pick n plus one integers, you can always ensure that there is an integer amongst them such that q value of that is more than n factorial by 2 to the n, 2 to the n, right? So how we finish is like we basically just uh, take like an integer d such that d factorial by 2 to the d has like modulus less than modulus, right? So what does that imply is like for q of x to be at most m, you need x to be at most m, sorry, mod x to be at most a, right? But for q of x to be at most m, you need q of x to be at most d factorial by 2 to the d. But there can be only at most. Also note that this is a sort of an increasing function. So like if you take d to be this, like right, and if n is at most at least d, then n factorial by 2 to the n is also at most at least d factorial by 2 to the d, right? So yeah, so at the end, you basically for this inequality to hold, you need mod of qx is at most d factorial by 2 to the d, right? And by the previous argument, we know that at most degree q values satisfy. Because if you take one more than degree q, then you would have this happening. Yeah, does anyone have any doubts from this? Yeah, does anyone have any questions from this or what we just did? Okay, I guess I'll just end here and like we'll continue tomorrow. So like tomorrow I plan to do like uses of like differentiation, some more applications, and two variable polynomials. Yeah. So I guess we will call it a day now. Anyone have any general doubts from the session? Feel free to ask.
Do we have lecture notes for this, like in the Discord?
Yeah. So what I did was like you already have like a very good comprehensive handout on polynomials Rohan wrote. right? So for theory purposes, you can always read that. What I did was like I made a sort of a problem set, right? It was more for myself rather than for you guys, like because I just did not want to forget stuff. So it has some extra problems which you can try. It's in the Discord announcement, right? It's not like a handout. It's more of a problem set. It has like the general heuristics I just told you about. As I said, mostly for me, I did not want to forget to say anything, and it has a more problems than I did in the session, so you can like refer to that.
Like the theory which you covered, where can we find this? Like, is it available on the
Okay,
server?
okay. I'll just like link Rohan's handout real quick.
Okay.
Uh,
Do you have a problem set like somewhat easier questions than
uh,
this?
easier is hard. No, I do not have like right now. It might take some while. Easier as in like, uh, can you like specify some particular level of problems that you are looking for?
Like maybe P1, P2 level.
Yeah, most of these today I just covered were like P1, P2 level. I think I like even the problem that was like a USMO problem I covered. It wasn't like a really hard uh like P6. It was a relatively easy P6. Yeah. Uh,
Okay. Sure.
Anything else?
I'll stop recording then.
Yeah. Also, I sent the handout I'm talking about to the resource share